picture of number 1. This is how it goes, folks. This is how this gets done. Gonna take a picture. There we go. I sent it. It's a pretty slick system, actually. So let's try some of this now. So remember, when we're doing this, we want to graph our, kind of like our parent function. We're going to graph y equals 3 times 2 to the x. Now this plus 1 in the end, we're going to realize that that shifts us to the left one. Whatever's being done to the x, it's the opposite of the sign. So it's actually like a negative. It's going to move things to the left one, or in a negative direction. And then this plus 1 after that is going to send things up 1. So I'm going to make that shift in a little bit, but initially I'm just going to pretend that this right here is the function, 3 times 2x. And that's the calculations I'm going to do. So, I know you don't have this much space on your room, but I'm going to actually write out the calculations. You don't necessarily have to, but you do need to know how to get them. So if it helps to write them out, do it. Now when we do these, we're going to insert the numbers -2, -1, 0, 1, and 2. So I'm going to start with 0. That's So you can start with whatever number you wanted out of those. So 3 times 2 to the 0 is the same as 3 times 2. Just kidding. Just kidding. 3 times 1, because 2 to the 0 is 1. And so we get 3. So I'm going to put that in here. And I could plot that point in. Then I'll do f to the 1. So, or f of 1. So I'm going to plug in 1 for x. And then I get 3 times 2 to the 1 is just 2. And that equals 6. Yeah, I think I need to order a new slate. Next, plug in 2 for x. So now we get 3 times 4, which equals 12. So this one is a 12. Now let's try the negative inputs. And it's not going to necessarily do what you think it's going to do. We'll see. So we take 3 times 2 to the -1. Now 2 to the -1 is the same as 1 over 2. Right? That's like a traitor. So we put it on the opposite side of the fraction bar. And that 3 is not a traitor. It stays right there. So this simplifies to 3 over 2, which is the same as 1.5. And then last but not least, let's plug in a -2. So 3 times 2 to the -2. That's going to be the same as, I'm going to write it over here. It's going to be the same as 3 times 1 over 2 squared, which is the same as 1/4, which is the same as 3/4. So this is 3/4 or 0.75. So then we just graph these dots, or these points, so -2, 0.75, -1, 1.503. Probably going to need that thing in a little bit. 1, 6, and then 212 would be off the charts. Now recall that these exponential growths typically just kind of level out. And if I kept doing negative numbers, folks, you would find that it never actually hits 0. It's going to hit some small values, but values that are greater than 0. So I'm almost done graphing it, but remember, we need to shift it left 1 and up 1. So all these points that I plotted, I'm going to move left 1 and up 1. Left 1, up 1, left 1, up 1. And this red line is actually the graph of the function. Now recall, this wasn't going to get above 0. But now that I moved it up 1, it's not going to, it's not going to get below 0. It's not going to get below 0, as you can see. Now that I moved it up 1, it's not going to get below 1. So when I fill in the domain and range, which I guess I cut off, the domain is going to be all real numbers, but the range is going to be y's that are greater than 1. Now I have a picture of number 2. So with number 2, we are again, well, let me do the shift first, or let me write the shift down. So that's going to move it to this shifts it left or right, but it's the opposite of the sign. So it's a -2. I'm actually going to think like +2, which would be 2 in the right direction, or right 2. And then this moves it up or down, but it's actually the sign. So it's a -2, so it's going to move it down 2 in a downward or negative direction. All right, so let's go back to just graphing this part. Y equals -2 times 2 to the x. So let's do, or our inputs that we'll always pick for exponential growth are these. So I'm going to take these in descending order, starting at the highest and going down from there. So -2 times 2 to the 2 is the same as -2 times 4, which is -8. When x is 2, y is -8. Now let me put in a 1. We get -2 times 2, which is -4. Oh, you know what, folks? These are numbered funny. So on my packet, it goes 1, 2, 3, 4, except for the 4 is a 2. So this is actually your last problem. So check that. Make sure that you are on the bottom. This is the bottom right problem on your packet. That's confusing. Sorry. Dang auto number system. Alright, so here's where things get goofy again, and I hope I didn't lose you last time. So we have -2 times 2 to the -1. 2 to the -1 is the same as 2, you move it to the other side of the fraction bar, so it goes to the bottom, and it's the same as 2 to the 1, which is 2. So this part goes down there. This 2, this -2, excuse me, stays where it is. It's not a traitor. So when you simplify this, you get -1, which kind of fits the pattern-ish. And then I say pattern-ish because it's not easy to see the patterns here other than the generalities. Things are growing or shrinking quickly. So here we're going to get the -2 on top out in front, this -2, and then 2 to the -2 is the same as 1 over 2 squared, which is 4. So this simplifies to -1/2 or -0.5. So let's plot it. Oops. Let's plot it. -2, -1/2, -1, 1. Boom. Boom. And I like using 2 different colors here. So this original graph will not cross the x-axis, so it's going to actually stay below y equals 0. However, now let's do this shift. So we're going to go right 2 and down 2. So every point here, and this one I found that it was easier to start from the right. I'm going to go right 2 and down 2. Right 2 and down 2, because over here points are going to start to kind of overlap. Right 2, down 2, right 2, down 2, right 2, down 2. Something like that. So yeah, there is an intersection there. And so now it wasn't going to get above y equals 0. Well, now that I moved it down 2, it's not going to get above y equals -2. Whoa, that wasn't the best curve there, but it isn't going to go to the right forever and the left forever, so the domain is all real numbers. Range-wise, it's going to go down forever, but it's not going to get above again. It's not going to get above y equals -2. So all the y's are going to be less than -2. Let's see what we have here for pictures. Huh, that's interesting. Just the same picture over and over. So let's do the real number 2 now. And I'll take a picture of number 3 while we're at it. Okay, the real number 2. Let's talk about our shifts first. We're going to be shifting to the left one because the x is getting added to 1, and we do the opposite of that direction on the x-axis. And then because the outside of that we have a +2, we're going to go up 2. Alright, so now let's talk about 2 times 3 to the x. So when x is 2, before we do that shift that we talked about, we would calculate this and we get 18. When x is 1, we're going to get 6. 1, 6 will be a point. When x is 0, remember our a value or our multiplier out in front of the base value is really going to be this answer because it's going to be 2 times 1 because anything to the 0 power is 1. So I didn't really need to do the math there. So remember here, this becomes a traitor, so that 3 needs to go to 3 to the 1 on the bottom. The exponent then becomes positive. So we get 2/3. Oops, I forgot to write down this coordinate. When x is -1, we get 2/3, which is like 0.66. For some reason, I like having it as a decimal when I'm trying to figure out how high or low to go. And then last but not least, for coordinates and inputs and outputs, we get 2/9 because again, this became 3 squared on the bottom and the exponent becomes positive. So that's the same as 0.22. So let's see, -2, 0.222, which is about 1/5 of the way up. -1, 0.666, which is 2/3, or 0.2. I guess it's funny I used a fraction then when I said it, but I think of it more clearly when it's a decimal. So there's kind of our parent function using the a value and the base, but then we need to shift all these points left 1 and up 2. Left 1 up 2, left 1 up 2, left 1 up 2, left 1 up 2. And so now, how it wasn't going to touch the x-axis or y equals 0, now that I moved it up 2, it's not going to touch the value or the line y equals 2. So my domain is all real numbers, but my range is the y's are going to have to be greater than 2 in this function. Let's try the last one. The shift is going to be left 2 and down 1. And then let's calculate our inputs, or our outputs given our inputs. So let's try 2. Let's see what we get. So we have -3 times 2 to the 2, which is going to be -3 times 4, which is -12. When x is 2, y is -12. Oops, let's do +1. -3 times 2 to the 1, we get -6. 0, remember when it's 0, it's just going to be that a value, the multiplier out in front, because this becomes 1. When I say this, I mean this becomes 1. Let's do some negative values. -3 times 2 to the -1. The -3 stays on top. This does not make it a traitor. This is just a negative number, folks. You've dealt with negative numbers for many years now. But the negative exponent sends things to the opposite side of the fraction bar and moves the or makes the exponent positive then. So we get -3/2. And then we get -3/4 because this becomes 2 to the +2 on the bottom. All right, let's plot them. -2, -3/4 would be most of the way to -1. -3/2 is 1.5. 0, -3. 1, -6. And then I can't fit the -12 on there. Now my shift is left 2 and down 1. So left 2, down 1. Left 2, down 1, left 2, down 1, and finally left 2, down 1. And so while this original function was not going to get above the x-axis, wow, that was a curvy one. Now it's not going to get, it's not going to get above the line y equals 0. Since I moved it down 1, it's not going to get above the line y equals -1. So it'll help us with our range. So the domain is all real numbers. It can keep going to the left and right forever, but the range is y is less than -1. All of our y values or outputs will always be less than -1.